再见你依然是少年的模样。这啥？这不是纳粹党的那个标志吗？还好对。这里有个鞋子。你在这里在看啥？好尴尬。跟他眼神交流，抬头也不是，不抬头也不是。从压低场。
Okay, you go to the canvas, right?
有点看一下。
Okay, I upload prepare course material in these folders. The syllabus. I guess I need to download to. Okay, this is the syllabus and the material instruction. Okay, two instructors teach the first half of the course. We'll try to finish up what we left over last semester. The new topics is that we'll use because other term will emphasize on the use of numerical method. So we'll start to use MATLAB computer, okay? And there's the big use of these numerical things to cover some new topics, okay? In particular, money and inflation, and also new models. So this is what we are going to do in the next few classes. Okay. So I guess these things is because it's numerical, right? So we use computer and so on. I think at the start of this academic year, we have a workshop on MATLAB, right? On MATLAB and Octave. So we're going to use these programs. We have sample programs and try to help you learn these things. Okay. Last semester we start with we already covered quite a lot of this socio-metric model, and then the Williamson lecture notes has a intertemporal version of the model, and then we'll just try to cover it. Again, I need to download. I asked you to read it now because we are going to cover very complicated things, right? So don't expect just by coming to lecture you will learn it just from me. It's just not possible. There's too many formulas, right? Many formulas and so on. I guess you cannot learn it that way. Unlike an undergraduate Econ 101. So you have to read the material. And I don't expect you to understand anything, and it's my job to try to help you understand the readings, right? Okay, so that's the target of the teaching. Okay, so I need to download all these lectures because my USB doesn't work. So you need to. I would strongly suggest you to print out the hard copies. Okay? Print out the hard copies and bring it to the class. Because when you learn these things, if you can write down something, go over some of the formula, it is a lot easier. Don't just look at it. I mean, I talk about it, but you don't get it unless you can write out something. So it's not a bad idea to prepare hard copies. Okay. Now the Williamson, okay, let me see. So we got everything on this folder. So there's also a paper, the Nobel Prize Committee paper. I try to explain. Session 3 is try to explain this model. Okay, the first thing we want to do today is to cover this infinite dimension version of the DMP model. Okay, so you look at these lecture notes. In chapter 7, right? So in chapter 7, we talk about the McCall model, and then the DMP model. We use the Williamson textbook. There's a one-period version of it, and we talked about it last semester. Okay, so yeah, so this is the DMP model, so the two-sided search model, but here is infinite horizon, right? So last semester we talked about the one-period model. Okay. So last semester we have the one-period model. Okay. Number 2, and then one period, right? So this one is what we talked about last semester. Okay, so the one period two-sided search model we talked about it last semester, and in particular the equilibrium of the model can be summarized by 2 pictures. Okay, so we use this picture to find out the equilibrium qualities of the model. So in particular, I modified the picture in Williamson a little bit. So basically, you have this picture. You have these 2 curves. They jointly determine the equilibrium wedge and the equilibrium market tightness. Okay. So once you have this wedge and tightness, you can back out other endogenous variable. Okay, so actually this part is a sort of the common features of the DMP model. So even though you go to the infinite horizon, we have a similar picture like that, in fact. So if you look at our lecture notes part 3, we have a picture something like this, okay. So in the one-period model, the wedge equation is a horizontal line, and here it is an upward sloping line, but the idea is the same, okay. So you have this so-called job creation condition or the zero profit condition, okay. The same idea as in the one-period model. And the wedge equation is a little bit different, but and then they make it upward sloping, but again, exactly the same idea. Just using this picture, you can determine the equilibrium wage and the equilibrium market tightness. Given these two items, you can back out all other endogenous variable. Okay, so this is one key result. And here in the something disappeared. Oh yeah. In the lecture notes. Okay. Let me go to. So in the infinite horizon version. Okay, so in this infinite horizon version, we have the workers at the firm, and they want to maximize lifetime utility. Okay, so here you have a sum from t0 to infinity. So the current time is time 0. Okay, so the firms and the workers are making decisions, and they are forward-looking. Okay, so this is a multi-period model. Now, this model differs from the one-period model that you learned last semester in that the labor force is constant. Okay, so in this version of the model, you only look at flows between unemployment and employment. Okay, so we don't look at flows in and out of the labor force. Okay, but in the one-period model that you studied last semester, you're actually looking at flows in and out of the labor force, and then given that, you look at how many people find jobs, and those people who don't find jobs will be unemployed. Okay, so in the one-period model that you learned last semester, the labor force is endogenous. But here, the labor force is exogenous, is fixed. Okay, I summarize a little bit in this lecture notes. Okay, so the first thing you have to realize is there's a fixed labor force. Okay, fixed labor force L. So just like the McCall model, right? So we have a fixed labor force. We don't consider labor force participation decisions. And then multi-period, right? So in particular, infinitely many period. And then we have the same thing as before, the matching function, right? So we use the matching function as a shortcut to characterize, to model frictions, right? Market frictions. Okay, so the matching function works like a production function, right? So just like a production function, but here you use inputs are people looking for jobs, and then also firms looking for people, right? Okay, so the number of unemployed workers, and then the number of vacancies. Okay, so these are the two inputs. But then with these people go through this random matching process, and then m number of worker job pair is produced. Okay, so those are match up workers and jobs. And of course there will be people who won't find jobs, and there are also jobs don't find workers. Okay, so these are unemployment, right? So at any time there will be people who could not find jobs, and they will be in the unemployment pool. And at the same time, there are also unfilled vacancy, right? So the unemployed jobs, may put it this way. Okay, so basically, as I said last semester, this model treats the firm and the worker symmetrically, right? So both of them can be unemployed. Okay, so the unemployment from the firm's point of view is unfilled vacancy. Okay. And then another key thing, right? So another key thing is that this matching function is assumed to be constant return to scale. And then this has very important implications. So by using the constant return to scale property, you can find that the job finding rate and the vacancy filling rate depends only on the ratio of vacancy and unemployment. Okay, so it won't depend on these two things separately, but it only depends on the ratio, which is known as the market tightness. Okay, and this actually makes the solution a lot easier. Remember the picture, we can actually reduce the model to just two equations using one picture, and then the intersection of two lines will uniquely determine the equilibrium tightness and the equilibrium wage. Okay. In Williamson, there's another way to determine the equilibrium. So a very similar idea. So basically you can reduce the entire model to two equations, and then again just using one picture. So here you have two equations that determine the total surplus and the market tightness. Again, the intersection of the two will uniquely determine the equilibrium market tightness. Right? So similar idea, but not the same approach. But again, the reason why you can get that kind of simple solution depends heavily on this constant return to scale assumptions. Okay? Without it, you cannot make this job finding rate and the vacancy filling rate depends only on theta. Okay? So this is a key, another key assumption in the DMP model. Okay. And as we explained last semester, this job finding rate, right? So this job finding rate, so this one is increasing in theta, right? So increasing in theta. So when the higher the market tightness, the easier for the workers to find jobs. Okay, so market tightness is the ratio of vacancy to unemployment, right? High theta means a lot of jobs, right? A lot of jobs, and therefore it will, for a worker, it is very easy to find jobs. And these two things, the job finding rate and the vacancy filling rate kind of move in the opposite direction, okay? Because both of them depends only on theta, right? Depends only on theta. But then one is depends positively on theta, the other is depends negatively on theta because theta takes the reciprocal, right? Take the reciprocal. So when theta goes up, these reciprocal things will go down, right? So therefore, you always have the two things move in the opposite direction. Good news for the worker is bad news for the firms, right? And vice versa. And again, this kind of so basically the as you can see here, if you don't have the constant return to scale, you don't have this kind of tight relationship between the two things, right? Because if you have U and V here, you have U and V here, there's no reason why they must follow this reciprocal relationship. Right? So this constant return to scale plays a very heavy role. But despite of that, you can see that it seems to be reasonable. So for one thing, we like this constant return to scale assumption a lot, because in the production function case, right? So we like this assumption. And then secondly, this will capture the idea of externality, right? Congestion externality and the thick market externality. Okay, so in a search matching framework, so there's a negative externality among agents of the same type, right? So the more workers are looking for jobs, it will make other workers more difficult to look for jobs. But then it will generate a positive externality on the opposite side, right? So the firm will find it easier to find workers. So this kind of model, this kind of search and matching framework has this externality, right? So this is well known to be. So this externality actually makes the equilibrium not Pareto optimal. Okay, so not the socially efficient outcome. Okay, because of these frictions in the market, and the source of this suboptimality is because of this externality, and we know that. We learned the social welfare theorem, right? So the first and second social welfare theorem, and those conditions that you need for the social welfare theorem to hold is that there's no externality. So if there's externality, there's a chance that so these two theorems will not hold, right? And this is one example here. Externality, right? Okay, externality because of these frictions. And in deriving the equilibrium, you also need this property. Okay, so as I said, the two things are related. Okay, so because of constant return to scale, right? So constant return to scale, you multiply these things in, you become this constant return to scale assumptions. So the job finding rate and the vacancy filling rate are not independent. Okay. And here's example. So we show you this. So it's not a bad idea to keep in mind a concrete example of the matching functions, right? So use this Kaplerkas matching functions, and you can see in closed form. So this is the job finding rate. Okay. So you set the first argument to 1, and then the second argument to V over U. Right? So the first argument set to 1, the second argument set to V over U, and then you can find that this job finding rate is indeed increasing in theta. Okay, and similarly for the vacancy filling rate, you can see because of this negative exponent there. Okay, so when your theta is high, it makes these things go down, right? So the vacancy filling rate is decreasing theta. So this is a concrete example. Then the externality, we talk about that, right? And the wage determination. So in this, the search and matching model, we abandon the Bayesian auctioneer, right? So the labor demand is not equal to labor supply. Okay, so you cannot make use of this condition to determine the wage. So you use some other mechanism, right? Not the Walrasian auctioneer to determine the wage. So here, in the DMP model, they use Nash bargaining. So assume that the workers at a firm will negotiate, which is actually more realistic than the Walrasian auctioneer. So in the real world, most of the time people negotiate when they do trade. Okay, and the outcome, right? So the outcome of the bargaining, is the same or can be described by the solution of this maximization problem. So basically the point, the idea is that it is not true the worker and the firm actually solve this maximization problem together. Okay, this is not how people negotiate, right? So basically the Nash bargaining approach says that after the firm and the worker negotiate, what comes out from the negotiation is the same as the solution of this maximization problem. Okay, so roughly speaking, the idea is that what Nash tried to do is that he write down a number of reasonable conditions for negotiation. Okay, and then show that if the negotiation process really satisfy all these reasonable conditions, then the outcome must be the same as this maximization problem. So the idea is very similar if you remember the social welfare theorem, right? The social welfare theorem. So we say, okay, there's a social planner, maximize the representative agents' utility subject to the resource constraint. And then social welfare theorem say that the solution of this maximization problem is the same as the outcome of a competitive equilibrium. So the idea is that in the real world, we have competitive equilibrium. People maximize their own profit, their own utility, and then they go to the market, and then suppose there's a demand and supply, Walrasian auctioneer, and so on, and then you have the competitive equilibrium outcome. So in the real world, people don't, there's no social planner, nobody actually solved the maximization problem, right? But then the welfare theorem proved that the competitive equilibrium outcome is as if there were a social planner solve a maximization problem. The same idea. So what Nash proved is sort of the same kind of idea. So this is a as if, right? So this kind of thing is as if, fictitious, kind of not real, okay? Fictitious. Okay. So now if you look